So yeah, inferences about two means from independent samples is what we're talking about here. So I guess my question to you guys is, what'd you come up with? What can we say is, what'd you guys learn in this class about independent versus dependent in statistics? Okay. So talking about whether variables depend or are independent of each other? Other ideas? You guys remember back in chapter 4 when we did the idea of probability, conditional probability, right? I remember a worksheet you guys did where we talked about choosing with or without replacement. Do you guys remember that? I remember we had the problem where we had Mr. Lemke picks a shirt from the rack and then puts it back. You guys remember that problem? When you have with replacement made things independent. And this was the situation where the probability of A given B was exactly the same as just the probability of A. Okay? But I do like the coffee example that Jamie was talking about. If we have men and women, okay, and we're going to compare the two populations. So yesterday we were comparing P1 and P2, right? This can work, but a dependent situation might occur when suppose we survey couples, married couples, for instance. That's a very dependent situation, all right? So that's tomorrow. This is going to be what we're going to talk about in section, I guess it's, what are we on? 9.4 tomorrow, okay? In section 9.4, we're going to take care of this very special case where things are dependent. But today, we really want the two populations to be independent. Otherwise, these formulas don't work. Matter of fact, I'm going to give you a list of requirements that we need, and you can take a look at them and pause, and if you have any questions about them, I'll take the questions. Here's the requirements we need for all of today's section. So yeah, we've talked about most of these ideas, and we've talked about number 4 before. I want both sample sizes to be bigger than 30, or you can get away with small samples if the populations have normal distributions. Like what kind of things have we studied that we know have normal distributions? Do you remember any ideas? Things that we know follow the bell curve? IQ score was one. Another thing that follows bell curve. What was it? Boy, I can't remember now. Do the Chips Ahoy chips follow bell curve? I'm not sure about that one. But the average does. The average does, because that's the central limit theorem. When you compute the mean number of chips, the mean of anything. If you have a large enough sample, the sample means will be normal. Heights, weights of people, okay, of adults, let's say. There's a lot of things that follow normal distribution. So sometimes you can get away with it. Test scores. Well, I guess we mentioned IQ test. Hey, have we seen that before? What is that? That is a formula for our what? What is it? It is. It's the t distribution, right? That's why we're using the variable t. This is the formula for your test statistic. Okay? So when we do hypothesis testing, this is the test statistic. It's kind of like the one I showed you yesterday, but the reason it says t is because we're going after the means. Hey guys, it says hypothesis testing. I have a question. What do you think would be the null hypothesis for this hypothesis test if this is the test statistic?
How can you tell if we don't have a number?
Yeah, well, that's a good question. How the heck can I tell? That's why I asked this question. It's not easy. Because normally what happens is I give you a situation, I make a claim, right? But I'm telling you that this formula would be useful for certain kinds of claims. Do you know what kind of claim I might be making here? That what's equal? Which means? Let's be very specific. Not quite.
x1 equals x bar 1 equals x2.
So this is the deal, right? I think this is an instructive question. Hey, maybe we should go back to chapter 8 for a second. Let's do that. Chapter 8. Tell me what the different null hypotheses looked like. You guys just took a quiz on it. What did H0 look like? Give me an example of what H0 might have looked like in chapter 8. What? Mu is equal to 76 inches or something, right? Or years, I don't know, mean number of something. Or population equals 50, and then majority would be greater than 50%, right? We talked about these things, right? So these are the kinds of things we have. I guess I'm really focusing on this, right? That's what the null hypothesis looks like in chapter 8. And the test statistic for chapter 8, I feel like I have those formulas somewhere here. Let me pull those up for you. So which one would we use most of the time? I guess it was this one, right? If you're going after a mean, you used to have this, right? So again, when you filled things in, right here, what were we going to put where that mu was? What? No, this is the x bar, see? It says x bar. I guess it's not big enough, sorry. Let me make that bigger for you guys. In chapter 8, isn't that the test statistic that you guys used for means? Right? Here's x bar, but where it says mu, what would you write almost every time? I guess you'd write whatever the mean was, right? So in our case, I guess it'd be 76, right? Okay, so maybe that's not so instructive. But I guess the point I'm trying to make here is that quite often we'll be talking about mean 1 and we'll be talking about mean 2. And quite often, and yeah, it's really fine print here. Let's make that bigger, huh? Oh yeah. On the fly. Ah, too big. Thought that was going to help. What is mu1 minus mu2 often assumed to be? 0. Because if mu1 minus mu2 equals 0, what's that saying to us? Yes. What is it that's the same? Which means we're claiming that what do mu1 and mu2 stand for? That's what I'm trying to get at here, I think. Mu1 and mu2, what do they represent? Population means. We don't know the population means. The only means we can compute are the sample means. The null hypothesis is going to be that the population means are equal quite often. And that means that mu1 minus mu2 is 0 quite often. Here, example time. Let's work through one. And then we can go to the homework if you guys want. Here's an example. I like this headline. Men and women are equal talkers. Look at the study they did. Number of words spoken in a day. Now, I've seen lately people talk about number of steps you need in a day. Any of you guys have that from work? Like they count how many steps you take in a day, the pedometer. What do they say you're supposed to get? 10,000 a day is what I've heard, I think. Am I right?
I think it's not around
Well, it looks like we're talking enough, right? 'Cause we have more than 10,000 words spoken in a day, right? Looks like the sample was done. They got 186 men and 210 women to participate. And we don't have all the data in front of us, but we do have some statistics, right? We have X1 bar. We have, what does S1 stand for? That's the... Yeah, what does that tell you, by the way? If the standard deviation is about 8,000 words, what does that tell you about the data? Think about it. The mean is 15,000, right? How many standard deviations away can you be and still not be uncommon? Like we said, within 2 standard deviations is not uncommon, right? So check that out. The mean is about 15,000, but the standard deviation is 8,000 some. That says to me, some people said they spoke like very few words, and some people spoke 30,000 words, you know? Wouldn't be uncommon to see that. So there's a big variety in how many words people speak in a day. So here's a question. Does there appear to be a difference from this study? Do women speak more words in a day than men do? Well, I don't know. That's what we're going to find out, right? So I'm going to pause the machine here, and this is your job. I want you to come up with an original claim, a null hypothesis, and an alternative hypothesis. Let's see if we can do that. Work with your partner and see if they agree. So what did you guys say is the original claim? Original claim? What's that? I don't want to say anything about P for this problem.
I said mean is equal to 50% or 0.05.
Yeah, I don't want to say anything about P for this problem, and let me explain why.
Oh, I said mean.
Oh, you said mean.
Yeah.
All right, well, let me come back to that. But first, why we don't want to say P is because my statistic that I have is X bar, right? So X bar estimates the mean, all right? Now, I want to be careful about saying the mean is 50%, because if I want to say percentages, I will use P. Here, for example, what's the sample mean? Well, it says 15,000, right? Or this sample mean was 16,000 some. Now, I don't know what mu1 is, and I don't know what mu2 is. But the question says, does there appear to be a difference, right? Does there appear to be a difference? The original claim, I guess, is right here. Men, women are equal talkers. I think how I would translate that, and let me zoom out a little bit, it's a little too big. I think how I would translate that would be the following. I would say something like, let's let mu1 be the mean number of words spoken by men in a day. let's let mu2 be the mean number of words spoken by women in a day. And so what USA Today said, the original claim on the newspaper headline, was basically saying that these are the same. mu1 equals mu2. That's what the data is saying. Any questions on that? Or, what's another way to write it? mu1 minus mu2, you could say, equals 0. Either way is okay for me. All right? But then what happens is you're going to have an H0 and you're going to have an H1. All right? Where's my claim going to go here? Definitely H0. That's equality. mu1 equals mu2. What kind of test are we going to get, guys? Two-tailed, because the alternative is going to be mu1 does not equal mu2. Right? That's the question. Does there appear to be a difference in the means? I have to pause. Let's go back to the problem. Right? And so after we have all these we have the claims, what's always the next step? What should I be doing next? The test statistic, right? So guys, what's the long way to do it? The long way to do it is to take each one of those pieces of data, and let me go back a couple slides, and put it in here. That's the test statistic. Are you capable of doing this? Yes, Paul. Do you want me to show you how to do it in class? No, Paul, we can do it just fine. Right? You want to see it? All right, watch. Yeah, here's the numbers. You want me to put it in the formula? You know how long that's going to take?
We gotta do it.
We have to.
Boom!
Want to see it.
There it is. Done.
I mean, it's pretty much self-explanatory. It's like
Isn't that beautiful? No, I'll tell you what I am going to do. I'll tell you what I do want to do. I want to show you how to do this using some technology. Let's use the calculator for this one. Let's use the calculator for this one. You guys have that calculator ready? It can handle all this stuff. We understand what these things mean now. I guess I want to spend more time on interpreting statistics and less time punching numbers. So, get that calculator out, and let's go back to that data set again. Where was that data? Here. And if I had the calculator out, I should be able to fill in the right stuff. I wonder if I can make this a little bit smaller so I can see both. Wouldn't that be nice? Yeah. That almost works. It just doesn't want me to do it.
Make the PowerPoint smaller to one side.
Oh, yeah, that's not a bad idea. Of course, if the PowerPoint gets too small, then you can't see the data anyways. Let's do that. Let's do that. Oh! Had it. Okay.
zoom in on the other one.
Well, I'll tell you what I'll do. You guys have that data written down?
No.
Well, let's write it down. 210, 15, 66, 8.5, 16, 215.0, 8632.5, and 7301.2. Yeah, guys, by the time I got done with that test statistic, it would have taken me a while. This is going to take long enough. Let's show you what to do with this calculator. Boom. I go to second distribution. Oh, no. Actually, what I do is you don't need the second button. Sorry about that. Second quit. Yeah, you just go to stat. So let's clear out some stuff here. Okay. Hit the stat button. All the way over to tests. You guys are getting better than I am. So now what?
0 plus sample, 2 sample.
2 sample. We want Z or T? We want t because we're going after means, right? You guys, when you do tonight's homework, I think section choice 3 there is going to be used, right? 2 sample z-test. Now let's do the t-test. Let's hit enter. Okay, do we have data or stats? We have, those are stats, right? Yeah, those are stats. Right? All this, those are statistics they gave me right there. Okay, so I'm going to go ahead and start entering. Enter some stats. Please. X1. Let's see. I guess that's 186, right? Oh, no, it's not. That says X bar 1. So that's the mean number of words. So that's 15, 668.5. That's the mean number of words that men speak in a day in our sample. The standard deviation we need also, that was 8632.5. How many men did we survey?
186.
Yep, that's N1. And now we're ready for population 2. Looks like 16,215.0. SX2 would be 7301.2. And how many women we surveyed was 210. This is where you have to select what is the alternative hypothesis. And we want two-tailed, so let me click on this. It didn't work. Let me try that again. Right there. Yeah, we want not equal. Okay, now, is the survey, is the sample data pooled, yes or no? I think we don't want pooled. Okay? Pooled would be if you know that the standard deviations are equal or something like that. But we're gonna say no. By the way, this arrow means that there's still more. So I'm going to click the down arrow here. Oh, it says blue.
I can't select two-tail. Do I press enter or what?
Yeah, you have to press enter on it. Yeah. It didn't work for me at first either. But maybe use the left arrow.
Black, just going over it.
Then you got it. And then when you press enter, it's supposed to
Scroll down. No.
Then go down a little more with the down arrow. You ought to get there. Okay, time for me to click calculate. Here I go. Look at all that stuff it gave me. So the very first thing it gave me was that test statistic. It said negative 0.675. Let me compare to what I did here on the PowerPoint. Not that I did this. Let's take a look. Is that what they got for the PowerPoint? Yeah. Negative 0.676, right? So it's nice that your calculator can do this quickly. Computers can as well. Let's see what else we have. What else did it give me? Oh, that next line. What's that next line after the t value?
P-value.
That's the p value. What does that tell us? That's a big p value, right? I don't know what the significance level is, but it's not going to be 49% or 50%, right? That wouldn't be much of a significance level. So what does this tell you then? Yeah, what's that mean? Let it fly. So the null hypothesis, we have, did we reject it or fail to reject it? We failed to reject the null hypothesis. This is the part that I think we still need work on. You see the p-value. You know it's high. I'd like you to talk to the person next to you about what's the final conclusion about this problem. I'll pause for a minute while you do that. Anytime you see fail to reject, we're going to start off our claim with there is not sufficient evidence. There's not sufficient evidence to warrant rejection of the claim that men and women speak the same number of words in a day. There does not appear to be a significant difference between the two means. Did we prove there's no difference? No, we can't prove that. But we haven't found evidence to say there is a difference, right? This is how statistics works. You can reject a null hypothesis, but you can't prove it. That's why the next sentence said there does not appear to be a difference, not in our data. Right? We don't have enough evidence to say much of anything here. It's a pretty big study, though. It's kind of interesting. Okay. Now, question, Amy, before I move
Can
on?
we go back real quick?
Sure.
What was the original answer after we did the calculator?
Let me go back to the calculator. See, because when we did it this way by hand, they got negative 0.676. And on the calculator, I got t as negative 0.6755. So that's pretty darn close. If you got a different t value, I'm going to ask you, look at the top. Does it say mu1 does not equal mu2 on your calculator? It should. Amy, what does yours say at the top? Or did you lose the screen? So again, in Chapter 9, not only are we going to do hypothesis testing, we're also going to do confidence intervals. I did this yesterday after the quiz. I said, hey, remember that example we had last week? Let's do it again with confidence intervals. So now that you guys look more awake and fresh than you did right after the quiz, let's try it again. How do you do this problem and construct a 95% confidence interval to estimate the difference between the mean number of words spoken by men and that spoken by women? Right? Let's estimate the difference. So, what's the old way of doing it? Well, yeah, right. So you're right that it seems like back in Chapter 7, if you heard 95% confidence interval, there were a couple things you wrote down right away. One thing, yeah, critical values, because you guys would draw this picture, right? You would put a 0.95 right in the middle. What else did you guys do back then? You did critical values, and then you knew that since, what's alpha in this problem? Yes, 0.05. And so you would put 0.025 here, 0.025 here. You'd get the critical values. You guys remember all this, right? And one of the reasons you needed the critical value was because you needed to compute, right? The way that a confidence interval works was the mean, mu, was going to be between two things. Do you remember what it was between? There was this thing, E, called the margin of error, right? And so you'd have x bar plus E, and you'd have x bar minus E. Yes? You guys remember that? Okay, what's going to change today? Today is we're going to estimate the difference, mu1 minus mu2. We're going to put it between two things. We're still going to have a margin of error, and the formulas get ugly. Let's take a look at the formulas, and you tell me, would you want to put all those numbers in? That's what you would get. It's all worked out on the slide for you if you decide you want to try it at home. I don't plan on doing it now. What I do plan on doing is doing it with the calculator, right? So let's use the calculator here. So let's see. The calculator, if I click on stats again, and if I go over to tests, I think they have a confidence interval test. Yeah, see down where it says choices 7 and 8? I showed you guys that last week. Look at choice 9. 2 sample Z interval. We don't want Z. What do we want since we're going after the means? There it is. Looks like on my calculator it's choice 0. I don't know if you all have this. 2 sample T interval. That's what I'm looking for. Now, if not, there's other ways to do this, right? But there we go. Oh, cool. It kept all the statistics in there. That's nice. On your homework for Chapter 9, they're going to ask you, hey, do a hypothesis test. Now with the same statistics, same data, do a confidence interval. So that's nice to know. It'll all be in there for you. Maybe I should double check, just make sure it's right. Yep. That first set of data looks right. The second set of data looks right. Oh, Down here it says sea level. What's that stand for? Is that good? Confidence level 0.95? Yeah, they don't say alpha. That would be significance level. Confidence level is 0.95. Pooled? No. I guess I'm ready. Calculate. That was cool. Takes a little time, but it gets it. So here's the confidence interval. They're saying negative 2,137 words to 1,044.4 words. They're estimating the difference. How far apart is the mean number of words spoken by men or spoken by women? From negative 2,100 to positive 1,000. What does that mean? Who speaks more words, men or women? I don't know. Okay, so this is what I can help you with, right? You didn't need me to help you type things into formulas today. What you need me for is, Paul, what does it mean? That's a confidence interval, right? So how would you write this down? You would write down, here, let me show you. I'll do it. This is the last line of the last page of notes that we have. Wow. New notebook next time. Here we go. So the 95% confidence interval, we could say our 95% confidence interval is, and it was negative 2,000 something. What is it? Okay. Negative 2,137 is less than mu1 minus mu2, because that's the way we did it. And that's less than, what is it? Thank you. Okay. I'll just round to a whole number. So suppose mu1 minus mu2 is negative 2,000. That would mean that mu2 is 2,000 bigger. This would mean that mu1 is 1,000 bigger, right? It could be negative, it could be positive. But guys, I think what's most important here, notice we may have mu1 minus mu2 is equal to 0. That's key. The fact that there's a negative number on this side and a positive number on that side means that maybe mu1 minus mu2 is 0. And what would that imply? Jamie, I didn't hear you. They're equal, right? We know that that's the same as mu1 equaling mu2, right? That's the point. We did a 95% confidence interval. And sometimes when you do it, the bounds of your confidence interval will contain 0. And if they do or if they don't, that says something to us, right? So here, the fact that they contain 0 says that there's not a significant difference between the two means. Does that make sense to you guys? Very cool.